Okay, we're back in part 2. So, case 1. In case 1, that is the case where the denominator of our rational function has distinct linear factors. In case 2, the denominator still had linear factors, but now they have powers attached to them. In case 3, this is the case where you factor the denominator and you get some linear factors, maybe, but you also get irreducible quadratic factors. So a quadratic factor is going to be something like this, something where the highest power is 2, and where it is irreducible. So meaning that this guy can't be factored any further. So as an example of something which is irreducible, x squared plus 1 is irreducible. You can't factor this at all. Really, x squared plus any number is going to be an irreducible, because you can't factor that without introducing imaginary numbers. And the way that this is different from the previous cases is that for every irreducible factor in the denominator, we're going to introduce one term into the partial fraction decomposition, but instead of the numerator being just a constant, now the numerator is itself a linear term. So an ax plus b for some constants a and b. So for example, consider this case here. So here the denominator is factored into a linear term and two irreducible quadratic terms. So the linear term gets a factor in the partial fraction, where the numerator is a constant. So this is the same as what we've been looking at. But then the irreducible quadratic terms, they get their own factors in the partial fraction decomposition, but their numerators have to be linear rather than constant. So that is the major difference. Aside from that, though, aside from the partial fractions being of a different form, the rest of our procedure is pretty much the same. In particular, when it comes to figuring out what these constants are going to be, we're going to be equating coefficients, like what we did over here. Okay. So, first off, let's see if we need to do a polynomial division. Well, we don't, because the degree of the numerator is strictly smaller than the degree of the denominator. So that's good. So we don't need to worry about that. Okay, so for the partial fractions, let's factor the denominator. So we get, well, we can just factor an x out of it. So we get x times x squared plus 4. And then that's it. That's the best that we can do, because x squared plus 4 cannot be factored any further. X squared minus 4 can be factored, right? X squared minus 4 can be factored. That's a difference of two squares. So that turns into x minus 2x plus 2. But a sum of two squares cannot be factored, at least not without introducing imaginary numbers. Okay, so we have a single linear factor and a single irreducible quadratic factor. So 2x squared minus x plus 4 over, and then I'm going to put in the factored form of the denominator. So a over x, so one term for our linear factor, and then bx plus c over x squared plus 4. So one term for our quadratic factor, but the numerator now has to be linear, as opposed to just a constant. And now we proceed pretty much the same way as before to figure out what a, b, and c are. So clear the fractions to get 2x squared minus x plus 4 equals... So for this first one, the a is going to cancel, but we're still going to have an x squared plus 4 left over. So be very careful now, because we're going to have to FOIL this dude. For this, the x squared plus 4 cancels, but the x does not. So we got that. And now, to figure out what a, b, and c are, we equate the coefficients. So first off, let's continue expanding the right-hand side here so that we collect together all of the like terms. Oh yeah, let me mention that. So collect the like terms on the right-hand side. Let's see. So if I distribute this through, I get ax squared plus 4a. If I distribute the x through, we get bx squared plus cx. And then, of course, let's get the like terms. So the x squared terms are a and b. The x terms are just c, and then the constant term is 4a. Now, let's equate coefficients. So the x squared terms, well, on the left we have 2, and on the right we have a plus b. So if these two polynomials are to be identical for every single value of x, then it must be the case that the coefficients are all identical. So 2 must equal a plus b. For the x terms, on the left we have -1, on the right we have c. So -1 equals c. Okay, well, that's easy enough. And then for the constant terms, on the left we have 4, and on the right we have 4a. Okay. And now we solve the system of equations. So we already know that c is equal to -1, so that's cool. If we take this guy and divide both sides by 4, we get that a is equal to 4. Or I'm sorry, that a is equal to 1. And then all we need to do is figure out b. So we know that a is equal to 1, so that means 2 is equal to 1 plus b. From which we get b is equal to 2 minus 1, so b is equal to 1. All right, so we got a, we got b, and we got c. And that is all of them. So now plug the decomposition into the integral. So this was the decomposition. Where a turned out to be 1, b turned out to be 1, and c turned out to be -1. Like so. And I can split this up a little bit further by turning this into x over x squared plus 4 minus 1 over x squared plus 4. Like so. And the reason I did that is because now this dude and this dude are amenable to the formulas that I wrote at the top of this document. So 1 over x squared plus 4, well, that's an arctangent immediately. As for this guy, well, you can do a u substitution. You can say let u equal x squared plus 4, and then, you know, do the relevant bookkeeping. This x drops out, whatever. Or you can just use the formula up here, this one.